My name is Professor Dukorata. We are continuing with our lectures in thermodynamics. Today we want to look at the lever principle. The lever principle is very important in terms of computation of the relative amounts of the liquid and vapor in a two-phase region in a binary system. That's the lever principle. That's the lever principle. Now, the lever principle is based on mass balance. It's based on mass balance. Based on mass balance. And like you have said, it is important for determining the relative amounts of liquid and vapor in a two-phase region in a binary system. Now, we start off by looking at pressure composition diagram based on Raoult's law. Raoult's law. Which is basically P1 is equals to P1 naught X1, where that is of the pure component P1 naught. P1 is of component 1 in the mixture, and the mole fraction of component 1. Remember, mole fraction of component 1, if you have, let's say, 3 components, the mole fraction, the sum of the mole fractions, let's say we have component 1 to 3, is x1 plus x2 plus x3, and this must all add up to 1 or unity. So that if you have 3 components, you only need to define 2 components, the third one will be implied. For example, if you know the mole fraction of 1 and 2, then the mole fraction of 3 is simply 1 minus the sum of the mole fractions of 1 and 2. So you don't need to define all the 3 components. Now, the pressure composition diagram, based on Raoult's law, we have pressure, we have mole fraction, 0, 1.00. For the pure component 2, that is the pressure. For the pure component 1, let us say that is the pressure there. And we have a liquid curve and we have a vapor curve. This is a liquid curve. And that is a vapor curve. Now, this liquid curve is linear. It's a straight line. So we know that for straight lines, very, very simple. To get the equation relating that, just compare that of a straight line. It's a very simple thing. A straight line, y is equals to mx plus c, where y coordinate corresponds to p here, x is the slope, and c is the intercept. So we have y, which is p, is equals to the gradient of the slope is p1 minus p2 divided by 1, that's p1 naught minus p2 naught, and the x-axis there, it corresponds to the mole fraction, and the intercept is p2 naught. P2 naught. That is the mole fraction. So that is the equation for that liquid curve. And of course, you can try that. That's for the liquid curve. That's the equation for the liquid curve. You can try one for the vapor curve. One for the vapor curve will be P is P1 naught, P2 naught over P1 naught minus P2 naught minus P1 naught Y1. Now, what is Y1? Y1 is the mole fraction of component 1 in the vapor. Mole fraction of component 1 in the vapor. It's mole fraction of component 1 in the vapor. Remember that. Now, let us work with this curve now. Let's work with this curve. So we have P, we have X. Let us choose a state point. So I'm trying to trace it up nicely. Let's have a state point which we call D. What's a state point? We have already in our thermodynamic discussions talked about very many state points, in the sense that a state point is defined by those thermodynamic variables. It can be pressure, volume, temperature. They define the state point. So a state point is defined by thermodynamic variables. So if you have this state point D, and you want to know, because remember the pressure, where pressure is, when pressure is high, volume is small. When pressure is low, volume is high. Boils low, boils low. So definitely at high pressure here we have the liquid, at low pressure here we have the vapor, and inside here we have both liquid and vapor. But that is liquid, that is vapor. So when we are at state point D, and you want to know the relative amount of vapor and that of liquid, how do we go about it? What we do is we draw what's called a tie line, joining the state point to the points on the liquid and vapor curves. Let's call that A, state point A. Let's call that state point B. Now, the line ADB is referred to as a tie line. The line ADB is referred to as a tie line. The line ADB is referred to as a tie line. Referred to as a tie line. Basically, it ties the state point D to those points, the liquid curve and the vapor curve. Sometimes you can talk of it as liquidus curve or liquid curve, but I prefer to use liquid curve and vapor curve because you don't have a similar decoration for the vapor. So we can talk of liquidus curve, liquid curve, but for the vapor we just talk of vapor curve. So for consistent, let's just talk of liquid curve and vapor curve. Now, let us see how we can get these relative amounts after drawing the tie line linking state point D to points on the liquid and the vapor curves. Now, the segment AD. The segment AD, if we call this segment as having a mole fraction for the liquid X1, and the segment D having the global mole fraction for the system, and here B corresponding the mole fraction Y1. Then, in terms of the length of this segment, we can express this length of segment AD in terms of these mole fractions, just like you can express the segment DB in terms of those two mole fractions. Now, AD is simply X minus X1, and the segment DB is simply Y1 minus X. Now, we need to define a few things. One, that X1 corresponds to the mole fraction of component 1 in the liquid over the total number of moles of the liquid. Y1 corresponds to component 1 in the vapor divided by the number of moles of vapor. And X is the number of moles of vapor plus that of liquid over N. Or we can just call it, let's call it N1 over N. leave it as N1 over N, make our life easy. N1 over N, where N will be the number of moles of liquid plus the number of moles of vapor. Now, how do we proceed? Let us put in these new definitions of the mole fractions in the expression for the segments there. The expressions for the segments there. Now, what do we have for AD? Now, we have that AD, segment AD, line segment AD, is N1 over N minus N1 liquid over N liquid. And segment DB is N1 moles of 1 in the vapor over the total number of moles of the vapor minus N1 over N. Not forgetting that N represents the total number of moles of liquid plus the number of moles of vapor. Let's simplify these expressions. Let's cross multiply by N liquid and cross multiply by N vapor. So let's call that expression 1, expression 2. So if we cross multiply expression 1 by N liquid, then we will have N liquid AD is equals to N1 over N liquid minus N1 liquid. And cross multiplying expression 2 by N vapor, we get N vapor dB as being equal to N1 vapor divided by N vapor minus we are multiplied by N vapor, so that N vapor is disappeared, minus N1 over N vapor. So if we subtract these two, these two quantities, what do we get? Very, very simple. So we are just doing some simple arithmetic here of just multiplying and subtracting. But the key thing is, one, we must know the mole fraction of the liquid that has the liquid component. If it's component 1, the liquid divided by the total of the number of moles of the liquid. In the vapor, the component 1, in the vapor divided by the total number in the vapor, and so forth. Very important for us to note that. Now, on subtraction, when we subtract these quantities, we get N liquid times the line segment AD minus N vapor and the line segment DB. This will now be equal to what? We need this space now. Let's see. That will be N1 to N1 over N liquid minus N1 liquid minus N1 vapor minus, that is plus N1 over N vapor. So we have just subtracted this quantity from that. So that's N liquid AD minus that. That becomes this first term minus that term. minus this term, minus crosses the minus, it becomes plus. And so let us look and see what makes our life easy here. So we have N1 over N, we can factorize it out, we get N liquid. If we factorize this out, this one, together with this, we get N1 over N in the N liquid plus N vapor. But remember, we had already said this is N, so it will cancel with that N. And then here we have minus N1 liquid minus N1 liquid plus N1 vapor. Again, remember, this is N1. So we are left with N1 minus N1, and that is 0. And this is N liquid AD minus N vapor dB bar. So, N liquid times the length of the segment minus N vapor dB is equals to 0. So we can just rearrange them so that we have N liquid AD is equals to N vapor dB segment. And so what do we have? Put the like terms together. So the segments AD over dB is equal to AD over dB is equals to N vapor over N liquid. Let's see what is the import of that particular expression there. Let's go back to our diagram. Let's go back to our diagram. Let's go back to our diagram. You have that diagram there again. Mole fraction, pressure, the liquidus curve, the vapor curve, liquid, liquid plus vapor, vapor. P2 not, P1 not. State point was D. Segment to say was A, D, B. Now, look at this. This is called the lever's rule. This is the lever rule. I'll call it lever's rule or lever rule. Of course, don't forget that we have lever also in the biological system, so they are different. There's the mechanical lever, and then you have the biological lever, which is an organ, which is a group of tissues together. And so, of course, you know that the organs together will form the system. So the liver is a fundamental system in the biological system, but that liver in the biological system is that. But this is the mechanical liver, so don't confuse the two, in as much as the pronunciation for them is the same. So this is the lever rule. Now, we have AD, segment AD over DP. That is the segment AD, and that is the segment DB. Now, pay attention. Segment AD corresponds to the moles of vapor. The length of segment AD corresponds to the number of moles of vapor. So, segment AD corresponds to the number of moles of vapor. This is vapor region. This is liquid region. And segment DB corresponds to number of moles of liquid. Segment DB corresponds to number of moles of liquid. That's a mnemonic of remembering the lever's rule, so that you don't have to go through the derivation. So that if you have your two-phase region in a binary system and you want to know the relative amounts, all you do is that state point, draw a tie line. What we call a tie line, like we did, we call that a tie line. Remember, that length, that linking D to the points on the curve, we call this a tie line. Just those of you who have forgotten already that we call a tie line. So you just draw the tie line. And once you have drawn the tie line, just remember, this segment represents that phase. This segment represents that phase. So AD represents, AD here represents the vapor phase. AD, vapor phase. DB, liquid phase. DB, liquid phase. And so actually, when you have the actual dimensions of these segments, you will compute correctly the number of moles in terms of vapor and liquid using Lever's rule. We'll stop at that particular point. We are going to pick on another thermodynamic principles and quantities.